In this lesson, we're going to cover a few different things. We're going to talk about linear approximations, and then we're going to talk about derivatives of absolute value and piecewise function. But we start off with a little bit of a review about tangent lines and our curves. And so they want us to, just in this little review here, do three things. Talk about whether the tangent lines would be above or below our function curve. Second, they want us to tell whether those tangent lines would have a positive or a negative slope. And then, thirdly, they want us to tell whether those slopes are increasing or decreasing, whether the rate of change is increasing or decreasing. So, let's take a look. We know that in this curve, our tangent lines would fall below our curve. So that's our first thing. Tangent lines are below. All right. Then we wanted to look at whether those slopes would be positive or negative. And of course, these here are going to have negative slopes. So these are going to be negative tangent lines. And as far as the rate of change, remember this is a very steep negative slope and a not so steep negative slope. So like a -5 to a -1/5. So these slopes are increasing. This is an increasing rate. All right. So our next curve, again, our tangents are going to be below that curve. No matter where I choose, the tangents fall below f of x. And these slopes are positive slopes. And our rates, if this one is a not so steep and this one is very steep and they're positive, so like 1/2 and +2 or 1/3 and +3. So these are increasing in value. All right, in our next picture, our tangents are above. Tangent lines fall above. And in this one, we have some positive slopes. So positive tangent lines. And in this one, we have a pretty steep to a not so steep. So like a +4 to a +1/4. So these are going down or a decreasing rate. And in our last picture over here, our tangent lines are still above. All right. These are going to have some negative slopes, so negative tangents. And this one is a not so steep to a more steep. So like a -1/2 to a +2. So -1/2, -1/2 to a -2. So -1/2 to a -2. Those are getting smaller, decreasing rate. All right, so that was really just for review. The only part of that we're going to be using for linear approximations are really about whether the tangent line is above or below the curve. And I'll try to explain why that's going to be important to our linear approximations and knowing whether our approximation is high or low as we go through the rest of our notes. But hopefully this is making a little bit more sense to you. All right, so let's look at linear approximations. It says that linear approximations are the use of the tangent line at a, f of a, as an approximation to the curve of y equals f of x when x is near a. So we're not actually using the exact point, but we're using some point that's near that point. So remember that our tangent line is a very close approximation for points that are near. It's as close as we could get, right? And so it's really still a very, very, very close approximation for the points near the point of tangency. And so what we're going to do is, since we know that this line has slopes, the closer I get in, the closer they are to the same slope here. The further I go out, the less I am close to this same slope on the curve. These two slopes are close to the same, but when I get out here, they're not the same as what the slope of the curve is. And so what we're going to do is write the equation of the tangent line, and then we're going to use that tangent line to find these points on the curve, except that we're actually going to use the line. So we're actually finding the value on the line and approximating that it's pretty close to the same thing that would be on the curve at that point. So it's on the line, but it's close to the curve. I think it'll make more sense once we do one. So let's just go ahead and try this. So here's how it works. They're going to give us some value that we want to use linear approximation for. So this is close to 3. So we're going to use a linear approximation for 3. So our function here, I'm going to go ahead and just distribute because I think that's going to be our easiest way to do this one. So 4x cubed plus x squared. Our derivative equation is going to be 12x squared plus x using our power rule. So we're choosing to use x equals 3 because it's close to this number. Because it's close to this number. All right, so we're going to write the equation of the tangent line at 3. So to do that, I need to know the value of the function at 3. So I'm going to plug 3 in here. That actually gives me 117. And then we're going to plug in 3 into our derivative so we can get our slope. And that is 114. So our equation would be y minus our y value equals our slope times x minus our x value. Okay, so this is the equation of the tangent line at 3. So if I were to, since 2.97 is very, very close to 3, then even if I use this line instead of the actual curve to find the output, it's going to be very, very close to the output on the curve. So I'm going to use my line to approximate the value on the curve. And so all that means is that I'm going to put 2.97 into this equation. So you may want to add the 117 over to the other side. So you have 114 x minus 3 plus 117. And then we're going to plug in that 2.97. So y at 2.97, or 114 times 2.97 minus 3 plus 117. And let me put that in the calculator real quick. All right, so in the calculator, we type all that in and we get 113.58. So the point 2.97, 113.58 is actually on the line, but it's also very, very close to the value that you would get if you plug 2.97 into the actual equation. All right, so here's what you get if you actually plug into the equation, the initial equation, 2.97. So 113.613, we got 113.58. So we are very, very close to that value. All right, so the second part of this, So we've used the linear approximation to find our value. This is what we got. But then the second part says, is this approximation high or low? Well, in order to know whether it's high or low, we need to know whether the tangent line at this particular point, or at 3, is on the top of the curve or on the bottom of the curve. And to do that, you've got to know a little bit about what this curve looks like. So that's why at the very beginning of the year, we went over some of the stuff that we did last year on curve sketching. So if I wanted to know a little bit about what this looks like, I could find the zeros of this. Remember, to find the zeros, you just set these factors equal to 0. And so this one just gives me x is 0. This one gives me x is negative 1/4. And so I'm going to kind of over exaggerate this, but negative 1/4 and 0 are where this graph is going to cross, and it is a positive cube function graph, so it should go down, up, and then double root at 0, bounce. So we were talking about using the tangent line at 3. 3 is going to be in this section of the curve. So like those things at the top, if I exaggerate that curve, that means my tangent lines are below. And if my tangent line is below, and again, over exaggeration, and this is at 3, when x is 3, and I just did 2.97, then 2.97 is here, and on the curve, it should have been there. So my value that I got is a little bit too low. It's always going to be too low when your tangent line is below the curve, and too high when your tangent line is above the curve. So to answer the question, part B, this approximation is too low because the tangent line is below the curve at x equals 3. You may be thinking to yourself, why would I want to make an approximation on the tangent line if I could just plug the number into the curve if I'm going to have to use a calculator anyway? Well, if it were without a calculator, this equation would be easier to solve than this one. Not that we're going to do it without a calculator, but they also can force your hand a little bit and force you to use this linear approximation. And so that's what our next example is going to show us. So in this example, they say, suppose that the only information we have about a function is that f of 4 equals negative 2, and the graph of the derivative is this graph that's shown. And it wants us to use linear approximation to estimate f of 3.9, and then determine if our estimate is too high or low. So if we're using linear approximation, we need the equation of the tangent line. To write the equation of the tangent line, we need to know x. Well, they told us we're approximating at 3.9, and so we're going to use 4. And the y value there is negative 2. The other thing that we need is our slope. But we know that our slope comes from the derivative. So all we have to do is look over here at this derivative equation, and on the derivative equation at 1, 2, 3, 4, when x is 4, our slope is 1, 2, 3, 4, 5, 6. This is 4, 6. And remember that this is x and then the derivative at 4, right? This equation here is a graph of the slopes. And so f of 4 is 6, so our slope here is just 6. So we're going to have y minus negative 2, so y plus 2 equals 6 times x minus 4. All right, we may want to move that 2 over so we can use our approximation. So subtract 2. So now we're going to plug in the 3.9. So we have 6 times 3.9 minus 4 minus 2. So 3.9 minus 4 is just going to be negative 0.1 minus 2. So 6 times negative 0.1 is negative 0.6 minus 2, or negative 2.6. And that's pretty easily done without a calculator. They forced our hand because we didn't know the actual function graph to plug in our 3.9. So we know that it's approximately a value of negative 2.6 on the curve. Now we have to also do our estimation of whether it's too high or too low. And in order to do that, we need to know what the curve kind of looks like. And to know what the curve looks like, we need to do a sign analysis graph here. So for our f prime of x graph here, we know that around negative 1 is where this changes. And so it was negative here. Then it changes to above, so positive. And then, I guess that's about 6.5. It changes again to down below. And so for our function, for the actual function, that's telling us that we're decreasing until we get to negative 1. Then we increase until we get to 6.5. And then we decrease again. So decrease, increase, decrease. So if I want to kind of sketch that, all right, so we're going to decrease until we get to negative 1. Then we're increasing until we get to 6.5, and then we're decreasing again. All right. So our point was at 3.9, or 4. And 4 is in this section right in here, which kind of looks like it's straight, but it's not. Remember, this is a curve, so I'm going to exaggerate that. A curve that's going like this. And so our tangent line was above, which means that our estimation is high. So it is too high because the tangents are above. The tangent lines are above. I guess I should finish that. Above f of x at x equals 4. All right, so now we're going to switch gears one more time. We talked a little bit about this the other day when we were talking about an absolute value function, and that we were always going to separate that into two separate equations, one for the positive slope and one for the negative slope. So when we get to these examples 4 and 5, that's what we're doing. But to kind of warm us up for that, we're going to look at this one, which is a piecewise function. They've already got it separated because it is two different pieces. And they want us to take the derivative. Well, all we have to do is take the derivative of each of those little sections. So f prime of x is just going to be the derivative of this function. So the derivative of that is just negative 2 for all of the x's that are to the left of 1. And then for the derivatives to the right of 1 is just 2x. However, you notice that this one says equal to. We cannot say equal to here because remember, you can't take the derivative at a sharp turn or at a cusp. And so just to make sure we understand what's going on here, remember this is just a parabola on the right hand side. So at 1, 1, we've got a point, and then at 2, 4, 3, 4, we've got a point. So this thing is curving like this. And over here on the other side, we've got this line that has a slope of negative 2. So up, 2, left, 1. It is a line going that way. And so right here, we've got a cusp. And so at that cusp, we can't take the derivative. So all you have to do is take the derivative of each of these pieces. Just leave off that equal to sign, because at where it's equal or where it's 1, we can't take the derivative. All right, so we're using that same idea to learn how to take the derivative of absolute value functions. And so for the absolute value of x, what we want to do first is rewrite this, because we know that the absolute value graph is really just two lines, one on the left with a negative slope, one on the right with a positive slope. So we're just going to separate this as x and negative x, x and negative x. And that change occurs at 0. So we're going to do x for the right-hand side and for the left-hand side. And for one of those, we want to put that it equals 0, because it really doesn't matter which one. But when we take the derivative, we know the derivative of this one, the top one, is going to be positive 1. For the bottom one, negative 1. But right there at the vertex, which is a sharp turn, we can't take the derivative, so we just leave it off. All right, and this last one is going to be the same thing. It's just that this time the graph has been shifted a little bit. So to know where it's been shifted so that we know where the vertex is, we just need to set what's inside the absolute value bars equal to 0. So 2x equals negative 1, x is negative 1/2. So negative 1/2 is where the vertex is located. And this one is still turned right side up, just like this one. So the right-hand side of our graph is still going to be the positive slope side. And so when we rewrite this function as two separate functions, the 2x plus 1 is going to be the right-hand side of negative 1/2, and the negative of 2x plus 1 is going to be the left-hand side of negative 1/2. Let's just spread that out a little bit. Okay, so when I take the derivative for the top one, I just get 2. That's for everything to the right of negative 1/2. And for the bottom one, I'm going to get negative 2. That's for everything to the left of negative 1/2. So taking the derivative is very simple for absolute value equations. But the first thing you have to do before you can take the derivative of an absolute value function is separate it into two pieces, or a piecewise function.